I will share the screen.
When you were saying something?
I was saying we will start at 3. Okay. Can you hear me?
Yes, ma'am. Assalamu alaikum.
Assalamualaikum. Okay, so we will start at 3 o'clock. It's 2:59 right now. So let's wait a little bit. So today will most likely be our last lecture because we'll hopefully finish today. Hopefully. Okay, so it's 3 o'clock. There are few students nowadays, I think. Okay, well, I think we should go ahead and start now. So yesterday we were talking about X-ray production and X-ray diffraction, okay? We will go ahead to do a little bit more about the X-ray diffraction part. Right now we were talking about the X-ray production, that if we have a device that's like this, okay? If electrons are accelerated from the cathode to reach the anode, they will bombard the metal over here, the target material, and they will produce X-rays. So we saw two spectra over here for two different materials, and this is for one material, tungsten, and as we increase the potential, accelerating potential, this is how the X-ray spectra is going to, the intensity of the X-ray is going to vary. And we had another one at another graph for X-ray spectra for two different materials at one particular accelerating potential, which is 35 kilovolts, okay? And we saw that this is the X-ray spectra as it appeared. So we see that there's some minimum wavelength at which X-rays are being produced. That is given by this formula. Today we will derive that formula as well, which is a small derivation. But basically, what we're saying over here is that we have this particular device, this device for X-ray production. And as electrons are going to bombard the metal, basically we're saying that the work function, remember before when we were talking about the photoelectric effect, so basically this X-ray production is the inverse of the photoelectric effect. Basically, photoelectric effect, when photons are bombarding the metal, are reaching the metal, and then when the energy of the photon is greater than the work function of the metal, it will emit electrons with the kinetic energy, with the maximum kinetic energy of the electrons being the energy of the photon minus the work function of the metal. Okay? So in this situation, the work function is only a few electron volts, whereas the accelerating potentials in the X-ray tubes are typically tens or hundreds of thousands of volts. So we can ignore the work function of the metal. Okay? So in this situation, the energy of the electron will be the voltage applied times the charge, right? Voltage times the charge is the energy of, you must have studied electrodynamics, right? And you know that if a voltage is applied to a particle which has a charge E, okay? The energy is the voltage times the charge, okay? QV. So QV is the energy of the electrons over here. That will be equal to H times H, so the maximum photon energy, as we're talking here, we're talking about the production of X-rays when electrons are bombarding the material over here. So the electron's energy is EV, V times the voltage times the charge. That is equivalent to the maximum photon energy that we will be ignoring work function here. As we said before, the work function is quite small relative to the voltage that is applied. So if we ignore the work function, the energy of the electrons is given to the energy of the photon. So the maximum photon frequency, maximum photon energy will be equal to VE, the energy that the electron will be giving the photon. So that will correspond to H times maximum frequency, because this is the maximum energy that the photon can get, which is equal to the energy of the electron, which is V voltage times the energy the electron charge. And then this will be equal to H. We know that frequency is equals to C over lambda. right? We know that frequency is equals to C over lambda. So I don't think I need to write that because that's very simple. So we know the relation between frequency and lambda and wavelength. Okay? Frequency is equal to C over lambda. So the maximum frequency corresponds to C over lambda minimum, because frequency is inversely proportional to wavelength, with C is a proportionality constant. So if we have maximum frequency, that corresponds to the minimum wavelength. So in this case, we will write 8C over lambda minimum, okay? And lambda minimum, if we rearrange this formula, lambda minimum, take this over there and this over there, lambda minimum is equal to 8C over V voltage times E, the electron charge. So if you plug in the values of the electron charge and the Planck's constant and the speed of light, you will get 1.240 times 10 raised to the power minus 6 voltmeter divided by the voltage. That is exactly the same formula we said yesterday, okay? And today we are doing the small derivation of that formula. This formula is known as the Duane-Hunt formula. Why? Because the scientists Duane and Hunt, they were the ones who determined that lambda minimum is inversely proportional to the voltage. So these are the two scientists who discovered this formula. That's why it's known as the Duane-Hunt formula. Okay, we know that it's the same as this formula, except different units. 2.11 kahan pe? 2.11. Well, we don't have that formula over here right now, so yeah. So X-ray production, we know that X-ray production is the inverse of the photoelectric effect. Basically, that is the inverse of the photoelectric effect. So we'll be doing an example here now. Find the shortest wavelength present in the radiation from an X-ray machine whose accelerating potential is 50,000 volts. So we will use, we want to find the minimum wavelength present in the radiation from an X-ray machine जिसकी accelerating potential है 50,000 volts. So 50,000 means 5 into 10 raised to the power 4 volts. इस formula में जहाँ पे हमारे पास ये formula था, we will put for V, the voltage, we will put in 5 into 10 raised to the power 4, and we will have this constant. In the Duane-Hunt formula, we will put this value in here, and then we will get the answer, which is 0.0248 nanometers. This is our minimum wavelength. And then if we want to find, if they're also asking us to find the maximum frequency that corresponds to this voltage, the maximum frequency of the radiation of the X-ray machine due to this voltage, we will find that frequency maximum is equal to C divided by lambda minimum, which in our case we found the lambda minimum. So C with the speed of light divided by this value, lambda minimum. So we will get 1.21 10 raised to the power 19 hertz. Okay? So that was the example here, and then we once the X-rays are produced, we can analyze the beam of the X-rays. If the X-ray beam, if the monochromatic beam of X-rays falls upon a crystal, it would be scattered in all directions. Okay? Because we said that crystal yesterday. We talked about the crystals that have spacing between the atoms. Okay? And the spacing between the atoms acts as a diffraction grating, okay? So basically when X-rays fall upon a crystal, basically consists of a regular array of atoms, so which can scatter electromagnetic waves because it acts as a diffraction grating. So when the beam of X-rays falls upon a crystal, due to the regular arrangement of the atoms in certain directions, the scattered waves will constructively interfere with one another. In other directions, they will destructively interfere. We already know that when light enters a diffraction grating, sometimes some places constructive interference will take place. In some directions, a destructive interference will take place. So the atoms in a crystal may be thought of as defining families of parallel planes. As we can see over here, this is like this distance is D1, this distance is D2. So they can have two sets of Bragg planes in a sodium chloride crystal is defined like this, okay? So basically, each family having a characteristic separation between its component planes. So basically, atoms in a crystal can be thought of as defining, there we have like Bragg planes, okay? Bragg is why we call it Bragg is because in 1913 Bragg was a scientist who talked about these planes, ठीक है? So इनके honor में ये planes were called Bragg planes, ठीक है? So basically each family of these parallel planes have a characteristic separation between its component planes. So we call these called Bragg planes, ठीक है? जिस तरह अगर हमारे पास ये है sodium, what is this over here? Sodium का crystal है, for example. Just 1 second. I just want to check because that diagram isn't so clear. Yeah, here we go. Here we go. What is this thing over here? This is not very clear from the diagram.
Chloride होगा.
Yeah, chloride होगा. ठीक है, so here we have sodium chloride and these also sodium chloride. This one has D1 distance and this one has D2 distance. So ठीक है, so this is like these are known as different Bragg planes because each Bragg plane will have a specific characteristic separation between its component planes. ठीक है? So these are known as Bragg planes. So now we already have done this many times before. We have derived the Bragg's law before, which is given by this formula. ठीक है? 2d sine theta is equals to n lambda. And the condition for constructive interference, we already have studied this many times before, is that when we have 2d 2 times, I think maybe I forgot to put that diagram in here. Yeah, this diagram, ठीक है? I think I should take a picture of this diagram. Sorry, I think I forgot to put this diagram in here. Anyway, so we have this diagram over here where if this is the incoming light, ठीक है, and this is the outgoing light. So यहाँ पे, as you can see, the difference between this light and this light is a path difference of 2d sine theta, because this if you have a theta over here, this is d sine theta and this is the d between the spacing between the two the spacing between the atoms in the crystal, ठीक है? This is our d, ठीक है? D. So this is our d sine theta and this is also our d sine theta. This distance here is d. This is our theta. So we have 2d sine theta is our spacing. So when 2d sine theta is when the separation, the path difference between this wave and this wave, ठीक है, is equals to 2d sine theta, when it's equals to an integer number times lambda. When it's equal to an integer number times lambda, then only constructive interference will take place, ठीक है? Why? Because in this situation, when constructive interference takes place, when the path difference between these two waves over here, when the path difference between these two waves is, which we know is 2d sine theta, when it's equal to an integer number times the wavelength of the wave, then only constructive interference would take place, because an integer number times the path times the wavelength will mean that the waves are a few wavelengths apart, but that means that they're still in phase. So that means the amplitudes will add, so we will get constructive interference. On the other hand, when it's equal to n divided by 2 lambda, then we will get that's the condition for destructive interference, because the lambda would be a half integer times, and when we have a half integer, times, like if this is the original wave, ठीक है? If this is the original wave, and when we have a half integer times this, then we would have the path difference would be a half integer, right? So it would be something like this, ठीक है? Because they're half integer times lambda apart. So that would cause the maximum destructive interference to take place. ठीक है? So this is our condition for the destructive interference. This is the Bragg's law, ठीक है? We already derived this. So basically you can derive this in 2 methods. This is one method by which you can derive it, or another method is the one we have done in a previous chapter, ठीक है? I think we did that in wave properties of particles. So we did that in one of the previous chapters. So you can derive the Bragg's law in any of those methods, ठीक है? So yeah, so that was about X-ray diffraction, and the X-ray spectrometer can be designed in this way. Basically, when we have when we have an evacuated tube here, we have a cathode and an anode, okay? The electrons will reach the anode, they will produce the X-rays. This is the diffraction grating, and then the electrons will reach the crystal, okay? This is not a diffraction grating. This is like a collimator to basically focus the light onto a beam. Collimator is to focus the light onto a beam, okay, and then they reach the crystal over here. Then they will diffract, and this is the detector over here. They will diffract. They will constructively or destructively interfere because this acts as a diffraction grating. And then we can get a detector that is rotatable, and then we can detect the X-rays reaching the detector over here. Obey TCAM, we can detect the X-rays over here. So basically, the detector, as theta is varied, we can vary the theta, TCAM. The detector will basically record the intensity peaks corresponding to the orders as we have in according to this equation. N is the order of the N is like the order of the maximum, because this equation just describes the maxima. So corresponding, the detector will record, as you vary theta, you vary the detector's position, okay? The detector will record the intensity peaks corresponding to the orders predicted by equation 2.13, okay? If the spacing between the Bragg, if you know what the spacing is between the adjacent Bragg planes in the crystal, then you can calculate the wavelength of the X-rays according to this formula, okay? If you know what the wavelength of the X-rays used is, and you know what the order of the maxima is, then, and you know what theta is also, then you can calculate d, the spacing between the crystals. So basically this formula is used to do calculations as well regarding the spacing between the crystals, the theta at which the maxima is occurring, the end and the order of the diffraction of the maxima, and lambda is the wavelength of the X-rays. Yeah, so that's all for X-ray diffraction, and now we will do our last topic, which is pair production. Any questions so far? Okay, no questions, so we will do pair production, and this is our last topic, and we have up till a couple of slides more, okay? Let's see now what do we mean by pair production. So basically, this is our last topic in this particle properties of waves, and obviously this is our last chapter, so we'll hopefully finish by today. So what do we mean by pair production? As we have seen in a collision, a photon can give an electron all of its energy. As we have seen in the photoelectric effect that when photons reach a piece of metal, then electrons can be emitted. So in this situation, a photon is giving electron all of its energy. That happens in the photoelectric effect, or only part of the energy, which is the Compton effect. Okay? When the X-ray, for example, strikes an electron, then the X-ray will lose some of its energy and will be scattered and with a different wavelength, and the electron will be recoiled with some given velocity. So that is a Compton effect. Okay? It is also possible for a photon to materialize into an electron and a positron. A photon to materialize into an electron and a positron, which is a positively charged. We know that a positron is a positively charged electron. It has the same mass as an electron, but it has a positive charge instead of a negative charge. This process is called pair production. Electromagnetic energy is converted into matter. Basically, we have photon is electromagnetic, carries electromagnetic energy, and that energy is converted into matter based on E is equals to mc square. So basically, how does this happen? When a photon, it comes close to a nucleus, and we need a nucleus we need to have a nucleus over here, and we will do the proof of that. Why we show that pair production cannot occur in empty space. We will do that. Basically, pair production is when a photon, it gets this electromagnetic energy of the photon gets converted into matter, it loses its energy, it becomes an electron and a positron. And it does so in the presence of a nucleus. We need to have a nucleus present there for conservation of momentum and conservation of energy to take place. We need to have a nucleus over here as well. Then this photon, when it comes near nucleus, it will be converted into electron and a positron by E is equals to mc square. It will convert electromagnetic energy into matter. So let's see now how we can understand this pair production. We have to understand that conservation by means of conservation principles. No, what they're saying here is that no conservation principles are violated. एक तो हम charge को देखेंगे. We know that photon is chargeless. So यहाँ पे electron होगा और electron has minus charge and positron has positive charge. So इन दोनों को balance करने के लिए zero charge होगा. At the end of the equation, we have zero charge because both are canceling each other. So we have zero charge, and in the beginning, we also had zero charge. So we can see that conservation principles are not violated. The sum of the charges of the electron and the positron is zero as the charge of the photon, as is the charge of the photon. Photon also has zero charge. The total energy, including rest energy of the electron and positron, the total energy including rest energy of the electron and positron equals the photon energy. ठीक है? So the total energy of the electron and positron will equal the photon energy. So energy is conserved. Linear momentum is conserved with the help of the nucleus, which carries away enough photon momentum for the process to occur. And we will do the proof of that in this example over here. ठीक है? We will prove that a nucleus is required for pair production to take place, because nucleus will help to conserve the linear momentum of the system. ठीक है? Because of its relatively enormous mass, the nucleus absorbs only a negligible fraction of the photon energy. ठीक है? Energy and linear momentum could not both be conserved if pair production were to occur in empty space. Basically, if the pair production was to occur in empty space, मतलब है कि यहाँ पे अगर nucleus नहीं होता, फिर both linear momentum and energy cannot be conserved. So that's why we need to have a nucleus over here for pair production to take place. So now we will do this example over here, then we will go over here. The rest energy, mc square for an electron or a positron, is 0.51 mega electron volts. Hence, pair production requires a photon energy of at least 1.02 mega electron volts. ठीक है? So because the electron or positron उसकी जो rest energy होती है वो 0.51 mega electron volts है, उसको अगर double करें तो we need to have at least as much as the double of that. So pair production requires a photon energy of at least 1.02 mega electron volts. ठीक है? Which is greater than twice that. अगर इसको twice करें तो हमारे पास क्या आएगा? 0.51 times 2. Anyone? I don't have a calculator over here. But this is basically greater than twice that, okay? Because 1.02 का half अगर करें, yeah, it is this one, ठीक है? It is, yeah, वही आता है. So any additional photon energy becomes kinetic energy of the electron positron. अगर photon की energy इससे ज़्यादा होगी, इतनी minimum चाहिए कि ये produce हो जाए according to the rest mass energy of the electron positron. इतनी हमें minimum energy चाहिए of the photon so that two of these can be produced. If the photon has more than this much energy, then that will go into the kinetic energy of the electron or the positron. Any additional photon energy becomes kinetic energy of the electron positron. ठीक है? So the corresponding maximum photon wavelength is 1.2 picometers. If you convert this energy according to E is equals to hf, and then hc over lambda, when you calculate the lambda, it will be 1.2 picometers. ठीक है? So the corresponding maximum photon wavelength, this is the minimum energy, so that corresponds to the minimum frequency, h times frequency minimum. And then that is equals to hc over lambda maximum. So that corresponds to 1.2 picometers of wavelength. Electromagnetic waves with such wavelength are called gamma rays. ठीक है? So this basically we need gamma rays for this pair production to take place. Gamma rays are found in nature as one of the emissions from radioactive nuclei and cosmic rays. We know that gamma rays, they have symbol gamma. They're found in nature as emissions from radioactive nuclei. We have already studied about gamma rays when we studied about the chapter of nuclear transformations and nuclear decays. ठीक है? And gamma rays also come. They're in the form of cosmic rays because they come from the sun as well. ठीक है? And from outer space. So the inverse of pair production occurs when a positron is near an electron. Inverse of pair production also, basically we can also have inverse of pair production. Just when electron comes near positron and it will emit a photon. They will get annihilated. This is called pair annihilation basically. a positron is near an electron. The two come together under the influence of their opposite electron charges. Basically, because they are attracted to each other based on their opposite electron charges, the two particles will come together. They will vanish, and with their lost mass becomes energy in the form of two gamma ray photons. So this is also possible. Again, we have the inverse of pair production, which is pair annihilation. We have electron. This is a positron plus electron. They get annihilated. Means they come together. Their mass gets vanished, and that mass gets converted to energy in the form of two gamma ray photons.
Ma'am,
Sorry. इसमें nucleus की requirement नहीं है. No nucleus or other particle is needed for this pair annihilation to take place. Okay? The total mass of this positron electron is equivalent to 1.02 mega electron volts. The total mass of the positron electron, and each photon has an energy of, and as it is, because we have the total positron electron total mass is 1.02 mega electron volts. Okay? Mass in the form of energy. And each photon has an energy of 0.51. As we mentioned before, that each of the electron, the positron, has a rest mass of 0.51 mega electron volts. So basically, since we have two photons, each photon will have energy 0.51 mega electron volts, plus half of the kinetic energy of the particles relative to their center of mass. If each of these two also, they will have some kinetic energy as well. So plus half of the kinetic energy, half of the total kinetic energy of these two particles, half of that will go into this photon, half of that will go into this photon. And the rest energy, which was this one, goes into each of the two photons. So the direction of the photons is such as to conserve both energy and linear momentum. We need to conserve energy and linear momentum as well in this pair annihilation process as well. And so no nucleus or other particle is needed for pair annihilation to take place. Okay? Before we had pair production, we needed a nucleus there to conserve the linear momentum of the system. Linear momentum cannot be conserved, and energy cannot both be conserved if pair production were to occur in empty space. But in pair annihilation, we don't need any nucleus or any other particle. So now let's do this example over here. This will basically show that pair production cannot occur in empty space. This will basically prove that we need a nucleus there to conserve the linear momentum. So we will use relativistic calculations over here, okay? When particles are bombarding, because obviously the gamma photon is being involved, or gamma rays are being involved, so gamma rays have speed of light. So we have to use relativistic calculation here. So by conservation of energy, the energy of the photon, which will be HF, goes into, so now we're doing this derivation for the pair production. So the energy of the photon is HF, and the energy of the two electron-positron pair will be, as we know that the energy is E, relativistic energy, is equals to gamma mc squared, right? We know this is our total energy. So total energy of it will be total energy of the electron and positron will be 2 times gamma mc squared. So we have h nu is equals to 2 times gamma mc squared, where h nu is the photon energy and gamma mc squared is the total energy of each member of the electron-positron pair. This is the total energy of the electron-positron pair. So we have a diagram like this. This is the photon. This is the incoming photon that has energy h, that has momentum h nu over c. Why h nu over c? As we had done before, because f is the energy and c for a massless particle. For a massless particle, we will have p is equals to e over c, as I mentioned in the last lecture. For a massless particle, p would be equal to e over c, according to the relativistic equation. I hope all of you remember this. Okay? So this would be E is h nu, so divided by c. This is the momentum of the photon. And then if p is the momentum of the electron and p is the momentum of the positron, both are equal. Okay? They would recoil with equal angles. They would be scattered at equal angles. So the linear momentum in according to in the x direction, it will be p cos theta and p cos theta. So we would have h nu over c as 2p cos theta, okay? So h nu, if we divide throughout by, basically the angles theta are equal so that the momentum will be conserved. The angles will be equal so that momentum is conserved. Okay, we will multiply throughout by c, this equation throughout by c, we will get h nu is equals to 2p c cos theta. So this is our vector diagram, and then now we know that we have this equation, okay, we have this equation, and then we will put p is equals to, we know that momentum, relativistic momentum is equal to gamma m v for the relativistic momentum, okay, for a particle. So it will be 2 gamma mv, okay? So basically over here, let me write some things over here. Let me write some things over here. Basically here we have h nu is equals to 2p c cos theta, ठीक है? इसमें हम इस तरह से लिख देंगे कि p we know is equals to gamma m v, और इस c को हम लिख सकते हैं c square divided by c, ऐसे लिख सकते हैं ना, because I mean it will give us c eventually, this will go give us, it will be, is equivalent to each other, ठीक है? Basically this equation is equivalent to this equation. इसमें हमने c square over c लिख दिया, यहाँ पे सिर्फ c था, ठीक है? So basically now what we will do is that we know that v over c is less than 1 because c, nothing can travel greater than the speed of light. Cos theta is also less than 1. So basically h nu is less than 2 gamma mc square. According to this formula, h nu is equals to 2 is less than 2 gamma mc square, but by conservation of energy, we require that h nu should be equal to 2 gamma mc square. Conservation of energy says that h nu should be equal to 2 gamma mc square. हमने ये यहाँ पे conservation of momentum को use किया है. So there's something missing here. So basically we're saying that because according to the linear momentum conservation, 2h nu is less than 2 gamma mc squared. But we need it to be equal to 2 gamma mc squared, okay? So basically, it is impossible for pair production to both conserve energy and momentum unless some other object is involved in the process to carry away the initial photon momentum. So basically, we're saying this over here, this whole thing over here proves that a nucleus is required for pair production to take place. Otherwise, we're not able to conserve the linear momentum and energy. We're not able to conserve both energy and linear momentum in pair production if we do not have another nucleus or another particle. So, any questions so far? It looks like we have reached our end of our PowerPoint, and basically that is all for our semester, and we have finished our syllabus officially, okay? So yeah, best of luck for finals, and I guess this will be our last official class, but I mean, if any of you want to have a question answer session, we have a quiz tomorrow, by the way. We have a quiz tomorrow on nuclear transformations, and tomorrow is our last class. And the next week, if you want to have a question answer session, or if you have some questions related to the course, or if you want to do a particular topic or revision of a particular topic, then you can request me in the group or something, and I can arrange for that. But that will be based on student requests. Okay, so are there any? Yeah?
What electives will you offer in the coming semesters?
Coming semesters, particle physics, which is for seniors, introduction to particle physics, introduction to quantum mechanics, quantum mechanics 2, which is also for seniors. I don't think I'll be teaching you all next semester.
Why, ma'am?
Because I'll be teaching 2 courses for seniors, 2 electives for senior batch, and 1 astronomy and astrophysics, which will be for the sophomores.
No, ma'am, I am talking about our seniority, when we will be in seniors.
It's mostly quantum mechanics 1 and 2 होता है. एक quantum mechanics 1 होता है fall में, quantum mechanics 2 होता है spring में, और introduction to particle physics होता है spring में. So these are basically electives: quantum mechanics 1 and 2 and introduction to particle physics.
तो particle physics में research भी करवाती है मैम?
Research abhi ho sakta hai, it's possible, yeah. But I'm not doing that much research right now because I have a lot of teaching to do. But sometimes I do have time for research, so I will do research. But I do research mostly in astronomy, astrophysics.
Oh.
But yeah, it's possible though. Yeah. Any other questions? Okay, let me download the attendance list. So yeah, that is all for our semester, and we have a quiz tomorrow, which is 23rd, yeah. And the next week will just be open for any student requests for a question answer session or like a revision or something. Yeah, that's all for today, I guess. We finished early. We finished early today. Yeah.
फाइनल के सिलेबस में सारा कोर्स होगा ना जब ये
Yeah, Sarah. And it will be closed book exam, okay? It will be closed book exam, and everything we have covered can come in the exam. Anything we have covered can be tested in the exam, okay? And it will be closed book exam on 8th of January, okay? For 3 hours. Okay?
Okay, ma'am.
Okay, ma'am.
Okay. So that's all. And if any of you have any questions, I will be uploading these. Videos as well. So I hope that you can all benefit from them, and you can download them as well. And then if you need to, and then you can always, whenever you have questions, you can always, we can always arrange for a question answer session or something like that, okay? In the coming week. So we have a quiz tomorrow. So yeah, I hope all of you are ready for that. And yeah, that's all from my side for today. Okay.
Ma'am, last quiz में question number 1 का अगर आप solution भेज सकते हैं तो.
Question number 1. Okay, I'll send the solution of that.
Thank you.
Okay. Okay, so that's all from my side. If anyone has anything to share, or then you may. Otherwise, we will call it a day. Okay. Okay, nothing. Okay, I will send the solution to the question 1 of the quiz in the group. And yeah, that's all. Okay. See you tomorrow on the quiz then.
Okay, ma'am.
Okay, Allah
Allah
Hafiz.
Hafiz. Allah Hafiz.
Allah Hafiz.
Allah Hafiz.